Yeah, I see some more people are coming in, so we'll wait a couple more minutes. Okay, I think we can get started. Okay, so in this meeting, more people are coming in, so we'll wait a couple more minutes. Okay, in this meeting, we're going to talk about another example paper review on memory channel partitioning. But before that, I think everybody should have their paper assignments based on their preferences ready, and also a time assignment also. Please follow the instructions that Mohammed emails in terms of any conflicts or something you may have. Hopefully everybody has gotten the paper that they really prioritized. I saw actually all people got either a paper that they rated as 8 or 7. So hopefully it should be interesting. And some of you rated multiple papers as 8. So that was useful in allocation, clearly. That helped. Okay. So I think all the logistics are clear. Anybody has any questions, let us know. Then I will proceed with this. I don't intend to take very long over here, but so feel free to ask questions, actually. This is, again, an old paper that we have done. And next week, hopefully, Mohammed is going to give you an example of some other paper. And I'm going to follow the same approach like we did last time. First, give a summary of the paper, and then provide analysis, and then have some discussion. But discussion is mainly guided by your questions. Of course, you didn't read the paper. I don't expect you to read the paper. So depending on what thoughts you have, feel free to chime in. Okay, so I'm going to cover this paper, Application of Our Memory Channel Partitioning. And the full title is Reducing Memory Interference in Multi-Core Systems via Application of Our Memory Channel Partitioning. And this was published at Micro in 2011. So it's been about 10 years, as you can see. I'm going to use some of the presentation slides my student Lavanya used at the Micro talk. But as you remember, we need to first start with the background, problem, and goals to set everything in context. And this paper also tackles main memory bottleneck. And main memory latency is long, as we know. Because of this long latency, core stall and performance degrades. And multiple applications in today's systems share the main memory. And this leads to inter-application interference on the memory channel. So when one core is transferring requests, another core can interfere with it, and these cores can delay each other. And this inter-application interference degrades system performance. And this problem gets exacerbated further due to increasing number of cores, increasing number of threads per core, or threads in general, basically. And that number is increasing much more so than the off-chip pin bandwidth that we can supply data into the chips with. So we have a limited off-chip pin bandwidth. So this problem is going to likely become much more severe in future systems, especially with data-intensive applications that keep accessing main memory a lot, of course. So the outline of this work, the goal of this work is to mitigate inter-application interference at the high level, basically. And to this end, it proposes an approach that's different from the prior approaches that tackled the problem, which is essentially mainly application of our memory request scheduling. And the first approach this work develops is application of our memory channel partitioning. And the second approach is to integrate this channel partitioning with a simple modification to the memory scheduler so that you can have integrated memory partitioning and scheduling that is more effective than both the previous approach and the first approach that this paper introduces. So that's the overall goal. Let me give you a little bit more background, as much as needed for the understanding of this paper. Essentially, main memory consists of banks. Each bank has a row buffer. There are multiple banks to enable parallel accesses, and each bank has columns and rows. It's a two-dimensional structure. And if you want to access a particular column in a row, you first need to bring the row into the bank's row buffer. There can be only one row you can bring into the row buffer because of the design of the bank itself. And then you select which column of data that you need to access through the memory controller. And then memory controller brings that data through the memory channel and passes to the processor and the L2 caches, L1 caches, etc. So this is how it operates. Basically, you access a row, and then so the accesses to the row buffer, accesses that hit in the row buffer. Row buffer is actually, it can be thought of as a cache. It's really caching the last row you've accessed in a given bank. And accesses that hit in the row buffer are much faster than accesses that miss in the row buffer in a bank, because the latter accesses require the memory controller to write back the row buffer into the bank and then pre-charge the array and open another row buffer, another row into the row buffer. So many systems use a variant of the FRFCFS memory scheduling policy, which is first ready, first come, first serve, which prioritizes row buffer hits over others. And all else being equal, it prioritizes older requests over others. And clearly, this policy is unaware of the inter-application interference, because it's really just looking at what's in the row buffer and what's older in the request queue of the memory controller, right? So in fact, this exacerbates the inter-application interference. An application that has high row buffer locality can deny service to an application that has low buffer locality for some time. An application that's more intensive in terms of the number of requests it submits to the memory controller can also deny service to another application that's less intensive for a period of time, because the prioritization policy favors the row buffer hitting applications and also intensive applications. Okay, so the novelty of this work is compared to prior approach that does application over memory scheduling, request scheduling. It basically proposes to partition the channels. Okay, let's take a look at the prior approach. In general, these prior approaches, there's a lot of work in this area, actually. This paper was published in 2011, and even at that time, there was quite a few works in that area. Now, the key idea is to have the memory controller monitor application memory access characteristics, and then rank applications based on memory access characteristics through some sort of ranking, and prioritize the requests based on this ranking. Okay. So an example, a state-of-the-art example at the time this paper was written, is thread cluster memory scheduling. And I'm going to talk about briefly at the high level what this does. It basically classifies the threads, hardware threads in the system at the memory controller level into two groups, memory non-intensive and memory intensive. And it basically forms two clusters of threads, and it prioritizes the memory non-intensive threads, because these threads, if they're not prioritized, they get delayed significantly behind the requests of the memory intensive cluster, the threads, and they lose performance significantly. And if you prioritize them, you don't cause a lot of damage to the intensive cluster, because these are very, let's say, light threads that don't require a lot of memory bandwidth, but you gain a lot because prioritizing these threads enables these threads to make a lot of progress in the computation that they're doing. Whereas intensive cluster, by nature, they're very memory bandwidth intensive threads. Prioritizing one request of them will not have a whole lot of impact on the performance of these threads, because they keep demanding a lot of bandwidth and requests from memory. Okay, so the thread cluster memory scheduling, sorry about that, basically employs different prioritization policies inside each cluster also to maximize throughput. The threads that are less intensive are given higher priority inside the non-intensive cluster. And to maximize throughput as well as fairness in the intensive cluster, there is a round-robin shuffling algorithm that is employed so that all of these intensive threads get their turns to access, to be highest priority in accessing memory. And this enables fairness across these threads, as well as good performance, good progress across these threads. And that shuffling clearly gives a chance to each thread to make progress compared to other intensive threads. Okay, that's the idea of thread cluster memory scheduling. And this way it optimizes for both throughput and as much as possible fairness, but it requires ranking of the threads, as you can see, and clustering of the threads. Okay, so the advantages of, in general, application-aware memory request scheduling techniques, they reduce interference between applications by request reordering. After the requests are in the memory scheduler, memory request scheduler, you can reorder the requests based on the characteristics of the threads. And as a result, they improve system performance, but they also have disadvantages, especially in terms of complexity they introduce to the memory scheduler. They require modifications to memory scheduling logic for ranking clustering and prioritization, essentially. And also, there's one other disadvantage. They cannot completely eliminate interference by request reordering. So you already have a bunch of requests in your memory controller. You just need to reorder them. You did not really reduce the load on your memory controller in some other way. So the key approach and the ideas of this work, let's take a look at them. The key approach is essentially very different. You have multiple channels and partition the applications to different channels. That's the idea. So let's take a look at what this means. So modern systems have multiple memory controllers. Each of the memory controller controls a different channel. And if you have one request going on channel 0, another request going on channel 1, there is no interference between them. These are different medium or media, let's say. And we are going to take advantage of this. This gives a new degree of freedom that enables mapping data across multiple channels. So how do current systems take advantage of it? Essentially, they don't necessarily take advantage of this non-interference property of different channels. They basically map data of the same application to multiple channels. That, of course, has some benefit, which is maximizing the memory capacity, bandwidth utilization, etc. But it causes interference between different applications mapped to the same channel. Basically, data mapping and current systems are unaware of the interference between different applications requests. So badly interfering applications can be mapped to the same channel, right? So the idea of this work is to partition the channels between applications such that, let's say, applications that badly interfere with each other are mapped, their pages are mapped to different channels so that they don't interfere with each other. This eliminates the interference between applications requests, which is nice. And we're going to see how the work actually does it. So let me give you an overview. So the goal is to eliminate harmful interference between applications. And the basic idea is to map the data of badly interfering applications to different channels. And there are two key principles the work uses to guide this mapping. First, it separates low and high memory intensity applications, and as much as possible, it maps them to different channels. Second, it separates low and high robot for locality applications, and as a result, and again, as much as possible, it maps these applications to different channels. And I say as much as possible because it's not always possible, right? You may have, let's say, 100 cores. Let's assume that you're doing it at the core granularity. Partitioning 100 cores, every one of them separately to 16 channels, let's say, is not possible because you have more cores than channels. So you need to actually have an algorithm that minimizes the bad interference that happens between applications. So to be able to guide that algorithm, the paper has two insights. These are not necessarily novel insights based on the paper, but the way the paper uses these insights to partition the channels is new. So high memory intensity applications interfere with low memory intensity applications in shared memory channels. This is a made up example. For example, we have a red application and blue application, and they're going to two different channels, channel 0 and channel 1. In the conventional page mapping, what might happen is that they interfere with each other. As a result, the blue application's last request gets serviced after 4 time units, and the red application's last request gets serviced after 5 time units, right? They both interfere with each other, basically. This could happen. Now, with channel partitioning, you basically say red application goes to channel 0, blue application goes to channel 1. There is no interference. As a result, in this particular example, both applications save cycles and improve performance. So this is one potential benefit. And if this works nicely without causing any other performance side effects from, for example, from the perspective of capacity or bandwidth utilization of the applications, then this is a net win. But of course, it may not always work perfectly. That's why you need to be careful about how you do this partitioning. So, but the first key insight is mapping data of low and high memory intensity applications to different channels enables you to improve performance, especially for low intensity applications. So you can see the savings on the low intensity application is a lot over here. And you can also potentially save on the high intensity application, depending on how you do the partitioning. Okay, the second key insight of the paper is to separate applications by robot for locality. And again, a very similar insight. High robot for locality applications interfere with low robot for locality applications in the shared memory channels. This is with conventional page mapping, where applications are mapped to different channels and they interfere with each other. And these are the row IDs that they access, as you can see. The red application happens to access row 0 multiple times, so it has better robot for locality in this picture. And it gets prioritized because of that, as you can see, because we have a robot for hit first scheduler. And as a result, these are the time units that these applications get serviced with this access pattern as an example. And if you actually partition these applications to different channels like we've done in the previous picture, the blue application that doesn't have good robot for locality benefits because it doesn't get delayed behind an application that has good robot for locality. The red application in this particular case doesn't benefit, as you can see, because it was getting the best performance it could given the access pattern it has previously. But still, you save cycles and you eliminate interference between the two applications. So these cooked up examples are nice, but they motivate why the decisions are made the way they're made in the partitioning algorithm. Clearly, world will not be as nice as this one because you're not going to have equal number of applications as the number of channels. Plus, the applications may demand more capacity than one channel can afford. Plus, they may actually need more bandwidth than one channel can afford, right? So these are all real concerns. Okay, but the second key insight still remains. We're going to guide the algorithm to map data of low and high robot for locality applications to different channels. Okay, so somebody mentioned this also seems like a possible prevention mechanism for side channels. That's a great insight, I think. I agree, yes. As long as you can separate applications that are security critical from security non-critical, let's say. And I agree, yes, because this is really providing you isolation at the memory controller level. So it eliminates the memory controller level side channels. Clearly, this may not eliminate the cache level side channels. You need to do something else for them. But whenever you isolate applications to different physical resources, you're really getting rid of the side channels between them. I mean, there may be other side channels through which you can gain information like power, shared power resources, etc. But at least the performance side channel, the latency measurement side channel is eliminated because you cannot observe, you cannot influence and observe what another application is doing based on the request that you inject. So very good, thanks. And this work doesn't deal with side channels though. In hindsight, it would have been interesting to actually deal with side channels. There are actually later works that were published in 2017, 18, 19 that look at similar isolation mechanisms to get rid of the memory controller level side channels. Okay, so let's now go into mechanisms in some detail. So the mechanism at the high level consists of 5 steps. The first step is to profile the applications and understand their characteristics, like we have discussed, robot for locality, memory intensity, and then classify applications into groups, partition channels between application groups, and then assign a preferred channel to each application, and then allocate application pages to the preferred channel whenever you are allocating pages. And then there's an optional step dynamically migrates pages between different channels, but that is not implemented in this work. Okay, so if you look at the proposal in the paper, it basically says only the profiling applications component needs to be in hardware. Everything else can be part of the system software. So in that sense, it's going to be less intrusive to the hardware to implement. And if the profiling data is already available in the hardware counters, then you don't even need to modify the hardware. Okay, so let's take a look at each of these steps. So profiling applications, you add hardware counters or use existing hardware counters to collect application memory access characteristics. And there are 2 major memory access characteristics that the paper proposes to collect: memory intensity in terms of last level cache misses per kilo instruction, and robot for locality in terms of row buffer hit rate, which is the percentage of accesses that hit in the row buffer. And these are relatively easy to collect, basically. If they're not already collected, in many systems, they're actually already collected. The second step is to classify, at least right now, they're collected. When the paper was written, they were not necessarily collected. Actually, they were not collected in many systems. The second step is to classify the applications based on this information that is collected. So the work basically proposes testing the MPKI first and classifying the applications based on low and high intensity. And among applications that have high intensity, you test the row buffer hit rates such that you create 3 different groups of applications: low intensity, high intensity with low row buffer locality, and high intensity with high row buffer locality. The work says that among low intensity applications, different row buffer localities don't matter that much. Okay, then the next step is to partition channels among groups so that you allocate a preferred channel for each application. So basically, we have 3 classes of applications, and we have n channels over here. How do we do the assignment? Let's take a look. So low intensity applications get allocated some number of channels, and high intensity applications get allocated some number of channels. And assignment of the number of channels is done proportionally to the number of applications in each group. Now, you could, of course, this could be a downside of the mechanism's implementation. Is this the right thing to do? Is this the wrong thing to do? Clearly, you can question these metrics, right? And this is what worked, but there could be other metrics that could work better, clearly. And I still don't like, actually, the assignment in terms of the number of applications in the group, because this by nature wastes some bandwidth, right? Because low intensity applications clearly don't demand a lot of bandwidth, but you may be wasting a channel for them, let's say. So we're going to try to mitigate that in some other way later on. Okay, so basically low intensity applications get allocated, let's say 2 channels in this case, because you have a bunch of those applications. And then we partition the applications between high intensity robo for locality and high intensity high robo for locality. Based on the robo for locality, we partition the high intensity channels, let's say. And that is based on the proportionally to the bandwidth demand of each group. Okay, we did not use bandwidth demand to partition between low intensity and high intensity because that's a bad metric for interference. You may actually group some low intensity applications with some high intensity applications if that's the case. But here, these are both high intensity. You can partition based on the bandwidth demand such that these channels go to low robo for locality applications, and these channels go to high robo for locality applications. Okay, so this is how it works basically, and the algorithm is in the paper. You can take a look at it for more detail. Basically, there are 3 groups of channels that are colored. You can think of this as channel coloring also, right? Very similar to page coloring mechanisms in operating systems, for example. And essentially, this is an operating system level coloring mechanism. Okay, now the next step is assign each application a preferred channel from its group's allocated channels. So how many channels has a normal computer today? It depends, I think. It's increasing, basically. It could be 4 channels. In more aggressive systems, it could be maybe 6 channels, 8 channels. I think going forward, they may increase. But of course, it depends on the system also. So if you go into a high bandwidth memory-based system, it becomes higher because you have more connections through the interposers. But if you're limited by 2-dimensional interconnect and normal DDR-based systems, then you're limited by your pin count a lot. Whereas high bandwidth memory, you're less limited by your pin count. You're limited by the interposer density that you have. And 3D stacked systems, of course, then you can have even more channels because you have many more through silicon vias. So going forward, the channels are expected to increase, but they're not going to increase as fast as the number of cores for sure, because these are interconnect that is relatively large. So it's not going to catch up with the logic density scaling that has happened over the course of 70 years. But that's a very good question. So in the paper, it evaluates, for example, with 4 channels. There may be other evaluations that I forgot, but I think a 24-core, 24 application and 4-channel-based system is the default evaluation, as we will probably see in a little bit. Okay. So the first step is assigning each application a preferred channel from its group's allocated channels. And the idea here is to distribute applications to channels such that groups' bandwidth demand is balanced across its channels. And we will see this with an example over here. So let's take a look at the low intensity group, assuming that you've assigned 2 channels to the low intensity group, and you have 3 applications that have respectively loss double cache MPKI of 1, 3, 4. The basic idea is to sum up the MPKI such that they're balanced across the channels. So this is a good example. Of course, summing up is not the best heuristic, but it's a simple heuristic. Basically, this is an MPKI of 4, let's say, and this is an MPKI of 4. And you're kind of balancing the aggregate MPKIs across different channels. And MPKI, in this case, is used as a proxy for representing the bandwidth demand. Okay. I mean, you could imagine other things, of course, over here, which I'm not going to talk about. Other metrics are possible. So now that this way, you do the same thing for the 2 other categories of channels for different types of applications. And then now the 5th step is allocate a page to the preferred channel. So we computed the channel preferences. Each application has a preferred channel now, and maybe also a second preferred channel. That's also possible. The paper doesn't talk about it, but it's clearly possible to generalize it. And now you enforce channel preferences computed in this previous step. So on a page fault, the operating system allocates the page to the preferred channel if the free page is available in the preferred channel. And if free page is not available, replacement policy tries to allocate page to the preferred channel. Okay. If it fails, it allocates page to another channel. Okay. Basically, this is a preference. It's not a hard constraint. It's a soft constraint. It basically says, if I can allocate from the preferred channel, I'm going to. If I cannot, then I'm going to allocate from some other channel. And clearly, you can also rank the channels, which this work did not do. But the mechanism can be extended, basically, depending on the constraints you have in the system. So one thing I should mention that this work slightly modifies the page replacement algorithm by making it more channel aware. But it doesn't go off all the way. Actually, you could do much better, in my opinion, by designing a customized page replacement algorithm based on the constraints of the channels that you have. But this work doesn't do that fully. It slightly modifies the page replacement algorithm by trying to allocate a page to the preferred channel as much as possible. But I think that there's more potential for replacement algorithms here that this work does not explore. We did explore that in an HPCA 2013 paper in a different context, and you can actually gain a lot of performance by making the page replacement algorithm channel aware. But again, I think there's more work to be done in that area to understand how the operating system should really allocate pages on the DRAM topology to minimize interference, and also allocate pages to minimize the page faults due to interference, etc. Okay, so at the high level, I've given you all the 5 steps. This operates on an interval basis. Essentially, you have a current interval in which you profile the applications. At the end of the interval, the operating system looks at the hardware counters. It performs steps 2, 3, and 4, classify applications into groups, partition channels between groups, and assign a preferred channel to each application. And in the next interval, it enforces channel preferences. Basically, it's really, as it gets page faults, it really allocates the page to the preferred channel of a given application, right? And in the next interval, you also profile the applications, and you do 2, 3, 4 at the end, which dictates what you do in the next interval. So what this work does not do is dynamic migration. So if, for example, an application changes behavior between different intervals, the work doesn't proactively dynamically migrate the pages of an application, because that causes a lot of churn in the system, actually. The migration is really not done. So the application may actually have pages in multiple different channels that are not preferred in the end. So we can actually discuss the implication of that, but migration is also very costly in terms of performance. That's one of the reasons why it's not done. Okay, so I see one question over here. I'm not sure if I understand RoBuffer very good. Is the RoBuffer a sort of cache? Yeah, you can think of it as a cache, basically. It's really a cache of a row. It's an 8 kilobyte cache. That cache is the last opened row. It's a large granularity cache also. And it's a cache that exists in all DRAM systems, basically. Okay, so let's now talk about how to integrate partitioning and scheduling. So this work, remember, the goal was to mitigate inter-application interference. Past work looked at request scheduling. This work introduced channel partitioning. And it realizes that the best is achieved by integrating these 2 techniques. So it integrates memory partitioning and scheduling. And the main observation that causes this integration is applications with very low memory intensity rarely access memory, and dedicating channels to them results in precious memory bandwidth waste. And the work does not want to waste bandwidth, basically. And also, these applications with very low memory intensity have the most potential to keep their cores busy. So it actually makes sense to prioritize them a lot. And if you prioritize them, they interfere minimally with other applications because they are very low memory intensity to begin with. And prioritizing them does not hurt others because of that reason. So the key idea of the integrated memory partitioning and scheduling mechanism is to always prioritize low memory intensity applications in the memory scheduler. Do not do channel partitioning for them, but use memory channel partitioning to mitigate interference between other applications that are more difficult to handle at the memory scheduler level. Okay, so we're going to look at key results now. Let's take a look at the methodology first, and then we're going to look at evaluation. So let's look at hardware cost first. So the key advantage of memory channel partitioning is it has very low cost. It doesn't change the memory scheduler at all. It requires only profiling counters and hardware, many of which already exist. And as a result, its storage cost is very small for a 24-core, 4-channel system, which is the baseline system that's used in this paper. And integrated memory partitioning and scheduling minimally changes the memory scheduler by adding a single bit per request that gets set if you want to prioritize that request. Essentially, this indicates that request belongs to a very low memory intensity application, and scheduler prioritizes based on the single bit. Okay, the paper simulates this approach on a simulation model, 24 cores, 4 channels, 4 banks per channel. And you can see the core model, etc. And it uses 240 combinations of spec CPU 2006 multi-program workloads so that it can have a good mix of different interference patterns in memory. And it uses the weighted speed up metric to measure system performance. So it compares to multiple different mechanisms, mainly on memory scheduling. FRF-CFS we already discussed. That's the major memory scheduling mechanism. And prior to this, other memory scheduling mechanisms that are application aware were proposed, like Atlas, that prioritize applications with low memory intensity at the high level. And TCM we already discussed, which always prioritize low memory intensity applications by grouping applications to 2 clusters, low intensity, high intensity, and shuffles request priorities of high memory intensity applications across themselves. And I'll just give you the main results of the paper. Basically averaged over, this is a big average, over many, many workloads. That's why the numbers are relatively small, because there are a lot of workloads where this doesn't matter because applications are low memory intensity and they don't even access the memory controller, for example. But when it matters, this idea actually works, according to what the paper shows. You can see that compared to a baseline system, FRF-CFS, it gets significant performance improvements just using memory channel partitioning. And if you use integrated memory channel partitioning and scheduling, you get more than 10% performance improvement. And compared to, yeah, we already said this, compared to the best previous mechanism, according to the evaluations in this paper, TCM, without adding much complexity to the memory scheduler, it gets better performance. So TCM actually is quite heavy in terms of the complexity that adds to the memory scheduler, as later works have shown. But this work actually simplifies the memory scheduler while providing higher performance. And if you actually modify the memory scheduler slightly, not as much as memory channel partitioning, you get even better performance, as you can see. So basically, it gets better system performance and the best previous scheduler at lower hardware cost. So the paper actually examines the interaction with memory scheduling. This is actually very interesting, I think. It basically looks at what happens if you implement IMPs, integrated memory scheduling, memory partitioning and scheduling, on top of different memory schedulers. And this is FRF-CFS, this is Atlas, this is TCM. And everything is normalized to the FRF-CFS over 240 workloads. So if you actually implement IMPs on top of FRF-CFS, you get a lot of performance, around 11%, as we've seen earlier. If you implement the same IMPs on top of Atlas, you get performance improvement. That's good, but you don't get as much performance as you would get over FRF-CFS. So these are, you basically lose performance compared to IMPs plus FRF-CFS. And that's true for TCM also, as you can see. Now, I think the takeaway over here is that IMPs, the integrated memory channel partitioning and scheduling, is really optimized for the FRF-CFS memory scheduling, because it really takes into account how FRF-CFS works, right? It really looks at row buffer locality and memory intensity, and FRF-CFS actually tries to prioritize threads like that. But IMPs tries to actually partition those threads to different places, to different channels, as well as it tries to also make sure that low intensity applications are prioritized, which is essentially against what FRF-CFS does. So basically, its principles are built on the downsides of FRF-CFS. That's why you gain a lot on FRF-CFS. So if you really want to do this partitioning nicely, and also maybe integrated memory partitioning and scheduling nicely on an Atlas or TCM type scheduler, maybe you need to build a different type of mechanism that takes into account the characteristics of those schedulers. And I think there's a really interesting, maybe fundamental work in that area to do that can potentially shoot up this number to somewhere over here. I don't know. We didn't do it. Okay, so highest improvements. So two conclusions: IMPS improves performance regardless of the scheduling policy, and but the highest improvement over FRF-CFS is actually highest improvement is actually gained over FRF-CFS because IMPS is designed for FRF-CFS. Okay, so let me summarize. Essentially, this paper tackled the problem of uncontrolled inter-application interference, which degrades system performance in the memory system. And it proposed the idea of application-aware memory channel partitioning, which consists of two key ideas. First idea is to separate the data of, overall basic idea is to separate the data of badly interfering applications to different channels, eliminating interference. And to this end, basically, it distinguishes between high intensity applications and low intensity applications, as well as high robot for locality applications and low robot for locality applications. And it also proposed integrated memory partitioning and scheduling, which prioritizes very low memory intensity applications in the scheduler, while handling other application interference by memory channel partitioning. And overall, the key takeaway is that MCP and IMPS provide better performance and application-aware memory scheduling at lower hardware cost. So now let me analyze strengths and weaknesses. Feel free to ask more questions or chime in. I'll start with the most important strength that I believe is the most important. So basically, this paper proposed a solution, a novel solution to a key problem in multi-core systems, which is memory interference, and the importance of the problem will increase over time. It keeps the memory scheduling hardware simple to solve this problem. It combines multiple interference reduction techniques, which is also interesting. It can provide performance isolation across applications mapped to different channels. And as one of your fellow students observed, this isolation can also eliminate side channels between those applications as well, at the memory controller level side channels, I should say. The general idea of partitioning can be extended to smaller granularities in the memory hierarchy, banks, subarrays, etc., as later work has done. Okay, these are the higher level. And then I believe it's a well-written paper. You can judge on your own. And the paper does thorough simulation-based evaluation. And you can see I omitted a lot of results, actually, that are in the paper for brevity. So weaknesses, again, this is where you need to be critical. I'll start with the most important. And I think most important is really about the mechanism. Mechanism may not work effectively if workload changes behavior after profiling. This is true for all dynamic or static profiling-based mechanisms. And this mechanism is not immune to that problem. Essentially, if the workload is high intensity and becomes low intensity in the next interval, too bad. Basically, you do the wrong thing, essentially. The second is overhead of moving pages between channels restricts the mechanism's benefits. Basically, we don't do that much dynamic page migration. In fact, not at all, because of this. So as a result, because the pages of an application may get mapped to different channels over time, mechanism's benefits may be restricted because of that. And there's a small number of memory channels in modern systems, and that reduces the scope of partitioning. I think going forward, this will become less of a problem, probably, with increased number of channels and interposer-based systems like HBM, and also 3D stack-based systems like future HBM and other 3D stack memories. But still, it's not the number of channels is not going to be as many as the number of cores and accelerators, for example. Load imbalance across channels can reduce performance. And that's true. That's a problem that the paper proactively tried to solve, right? It says, oh, we put these low intensity applications to these channels, but these channels don't get utilized as much. As a result, because you don't get these utilized that much, you may actually cause load imbalance. Yeah. And the paper addresses this and compares to another mechanism. There's more actually in the paper that talks about this load imbalance. There are actually mechanisms that were proposed to increase load balance in multiple memory controller systems. And you can take a look at the paper. And the proposal actually outperforms that system if you look at the evaluations in the paper. Okay, now let's go into the next step. A software hardware cooperative solution. That's clear this is a software hardware cooperative solution. And whenever you modify more than one layer in the stack, adoption becomes harder. And that's true for this mechanism as well. You could say evaluation is done only in simulation. And now we're getting into evaluation rat holes potentially. And that's also true. Evaluation is really done solely in simulation. And as a result, maybe not all of the overheads are completely taken into account. But again, when this work was done, there was no way of doing this evaluation on a real system because you cannot get these values that the mechanism needs from the hardware profiling counters. Later, actually, memory channel partitioning is employed in some systems. So people use similar metrics. And also hardware counter support became better for the memory controller level. At some point, there was no robot for locality-based hardware performance counters, for example. Evaluation doesn't consider multi-chip systems, and that's true also. Again, if you have multiple chips, we don't consider them. And that could be interesting also, clearly, right? If you have a more bigger distributed system with multiple chips, then you may have interesting issues like latency issues to different memory controllers also. And this doesn't consider them, right? Are these the best workloads to evaluate? Of course, there's always that question, right? Is it... I think the work does a good job in terms of selecting general purpose workload without biasing the workloads, but there are always more workloads to evaluate, right? Okay, and this may go into more performance analysis rat holes, of course, which we're not going to go into. Now, let me see. There are some questions. I'd like to try to take a cut at them. So one question asks, does averaging many applications not hide potentially significant drawbacks for some applications? Should we not also present worst case data? I ask because regular end user systems seem to have many low intensity tasks with low effective robot for reuse, and a handful of high performance applications with good robot for reuse. This seems counter to preferring low intensity tasks, which may destroy performance of the interesting high intensity tasks. So I'm not sure if I understand the question fully. Basically, I mean, certainly some applications may lose in this case, and the paper mainly evaluates system performance. So the paper doesn't consider like fairness in this particular setting over here. But yes, I mean, certainly some applications may lose because of this, but the overall system may gain. So this could be useful in a setting certainly where applications where your goal is really to improve overall system throughput in the applications. So other papers look at maximum slowdown type of metrics. I don't remember if it was actually explored in this paper. It might be good to check. If it's explored, then I think looking maximum slowdown is a good metric that looks at whether overall you lose a lot. But in terms of per application analysis, there's some analysis in the paper. But again, the goal is not really to provide quality of service guarantees for different applications. But I think the idea can be used for quality of service guarantees as well. This particular mechanism of memory that does memory channel partitioning is geared towards high throughput, assuming all applications are somehow equal. But if that's not the constraint that you have, if some applications are more important than others, certainly you can try to prioritize providing more channels or isolating those applications to some channels based on just that priority information, right? So I think even though the mechanism that's proposed in the paper doesn't take that into account, I think the general key idea of the paper, partitioning the channels, can be combined with a mechanism that takes that information into account. So that's very good. So there could be different ways of partitioning channels across different applications. And this paper proposes just one way to maximize system throughput. Okay, I wonder if we apply this to consumer systems, there's a current trend, mostly web-based applications. In that case, that would be potentially highly dynamic. Yeah, I don't know. I mean, that needs to be evaluated basically, how well the system works. But again, overall, this helps the throughput, but this may actually not help a given application that you really care about in the end, right? Okay, so and then there's a question about which how do you identify applications? How do you distinguish them? And again, that's again a design choice, I would say, that needs to be tackled also. Another question was the overhead of recomputing partitions and each interval evaluate against the marginal benefits for shorter intervals. How is the interval chosen? I think I will refer you to the paper. Certainly, the paper doesn't use short intervals because shorter intervals leads to overheads clearly. it uses longer intervals for that purpose. I don't remember the sensitivity to the interval length. It's either in the paper or in an extended version of the paper. But yes, certainly in any type of, but this is not necessarily new. Basically, in any type of interval-based mechanism, you always have the choice of choosing the interval length, right? If you choose the interval length too short, you may not really capture the phases, and your overhead might be high because you keep regrouping the applications, right? But if you choose the interval length too long, you may not capture fine-grained phases, but you keep your overhead low. And also your adaptivity may be low, right? So it's a trade-off in the end. And if you have a fixed interval size, there's no best way of really choosing it other than empirically. And the paper does that empirically, basically, like many interval-based systems. I think using adjusting these properties in some dynamic fashion is a good idea, potentially. Potentially, you can use machine learning to choose the characteristics of your algorithms, right? Like a lot of machine learning works do, but that comes with its own overheads also. So in a sense, there's no, in a sense, great way of designing an interval-based mechanism. You're always bound to make some empirical design choices unless you guide it through machine learning, which makes those empirical design choices automatically and dynamically. But again, it comes with its own overheads. So these are all good questions, I think, that are really mechanism-based. Okay. Yeah, and keep them coming. If you would like to speak to the microphone, that's also fine. If I may not answer you the question, or if I might interpret the question accurately, that might be a good idea. Okay, so let me talk about extensions. Basically, can this idea be extended to different granularities in memory, like bank partitioning, subarray partitioning, mat partitioning across workloads? And the idea is yes. And I think if you extend it to smaller granularities, you get better benefits, frankly, because channels are a very coarse granularity, although they're the easiest to manage granularity at the operating system level. But I think if you go down to smaller levels, smaller granularity levels, you can gain even more benefits because you become more finer grained. Can this idea be extended to provide performance predictability and performance isolation? This is actually related to one of the questions that were asked. So if you really care about the predictability of your performance for an application or the performance isolation of one application, can you extend it? And the idea at how, I believe it can be. Again, you just need to design a different mechanism based on memory channel partitioning, and grouping of the applications cannot be based on robo for locality and memory intensity only, right? You need to take into account what is the performance predictability that I want to achieve, what application I really care about to isolate, etc. Similarly to the security-based isolation that we discussed earlier, right? Clearly, you want to isolate a security-critical application from other applications. So you may want to dedicate a single channel to that application, for example, so that it executes in isolation in the memory controller. Okay, how can memory channel partitioning be combined effectively with other interference reduction techniques? The paper does kind of with scheduling, but there's an open question about source throttling methods. So source throttling is another way of actually reducing the load on the memory system and ensuring that you don't have, you reduce interference. Thread scheduling methods at the operating system level. Again, I think there are interesting questions over here, which I'm not going to tackle, but there could be a lot of extensions over here. And then can this idea be evaluated on a real system and how? And I think there are later works that have done this on a real system and shown benefits with memory channel partitioning across different applications. So let me do some takeaways very quickly. So these are the key takeaways, my takeaways from the paper. Feel free to chime in again. I think this paper introduced a novel method to reduce memory interference. I mean, today it's not novel anymore, of course, but at the time it was novel. It's simple and effective, and it can be used for many different purposes. I think that ties into number 4 over here. This paper used it for throughput improvement purposes, clearly. It's hardware software cooperative. This could be good or bad. I think of it as good, but clearly adoption is harder whenever you modify both. And there's good potential for work building on it to extend it to different structures, different metrics. And you can see a lot of bank partitioning work. I didn't really follow a lot of the works in this area, but there's some software work that built on it, as well as there's some hardware work that built on it to do bank partitioning. And I think the bank partitioning works are actually clearly an improvement over this work that basically show that by doing this at the finer granularity, you gain more benefits, but of course your overhead also increases. So nothing comes for free. And I think this is an easy to read and understand paper overall. So I think right now, let me open it for discussion. Feel free to chime in. Any thoughts you have on the previous ideas? Any thoughts you have on the practicality? I think we kind of covered, will the problem become bigger and more important over time? I mean, you can question this also, but I think my perspective on this is the problem will only become bigger because we're not really solving the memory bandwidth bottleneck as much as we really want to. There are benefits of 3D stacking systems, but they're not keeping up with the speed at which we can add demand for bandwidth. And I think both problem and solution, in my opinion, will become more important over time. Are other solutions better? I think this is an open question. Certainly, this is not, I don't think this should be used in isolation by itself. And is the solution clearly advantageous in some cases? Okay, so there's one input that I have. Let's see. So this is a more general idea. It seems that in many cases, interconnection of the memory seems to be something that could open up many optimization options. I wonder if something similar to what AMD has done with their Infinity Fabric could be extended to memory, allowing efficient memory movement between all locations. In that case, this might make it easier to dynamically relocate data and optimize. So actually, I'm not sure what you're referring to with the Infinity Fabric. Maybe you can tell us a little bit more. By the way, feel free to speak up. That might actually make it more interactive than me reading what's written. So certainly, if you expose more of the interconnection of the memory fabric, you can enable better optimization. Or if you can enable more data moment capability, faster data moment capability, let's say, between different memory modules, within a memory module, but certainly between different memory modules in this particular channel partitioning case, then you can gain more benefits. Okay, microphone broke. So if I understand the gist of your idea until you fix your microphone, I think if you have better connectivity between the memory controllers, such that you can migrate pages better between the controllers, like 3D stacking, for example, if you have better connectivity between different memory channels that are partitioned across different parts of the stack, or different portions of the stack, then actually, again, you can move data more easily that way. So those kind of improvements certainly help this sort of ideas that rely on allocation or relocation of data for sure. Yeah.
Okay, can you hear me?
Yes, yes.
Ah, wonderful. Okay, so no, the idea that I had was because like in AMD's current system, or I don't have a deep knowledge about it, but as far as I understood it, they like what they currently do in their EPIC system is they have like 8 CPU chiplets that can all talk to each other over this Infinity Fabric. So if we could extend this to memory, like have multiple memory modules that could all talk to each other and not always have to go through the memory controller, wouldn't that open up a ton of optimizations options, which would allow easily moving memory between all possible locations?
Yeah, I think I agree. That's true actually. Basically that way you can move data directly between the memory modules in some way without causing, let's say, a lot of churn in the system. So I agree. But of course, it requires some implementation of this interconnect in a nice way. In a two-dimensional system, I think it's a bit tougher to do between memories because you have to have some sort of memory controller to go through. I mean, it's true for a three-dimensional system also, but if you have a three-dimensional system, let's say you have a logic layer that connects 3D stacked memory layers to each other, and then you go through the logic layer, because you can go through the logic layer much faster because you don't need to go off the memory chip, then I think you can actually move that data much more quickly. So yes, I think it depends on the implementation, but yes, if you have that sort of interconnection between memory chips that do not disturb the CPU, certainly I think you open up a lot of optimization by moving data directly between different memory chips. And I think certainly memory channel partitioning can become nicer as well because you can dynamically migrate data much faster without disturbing the CPU. Cool, very good. Any other thoughts, questions? discussion? Okay, I see one more thing. Okay, to partition memory channels makes sense to me, but I don't see the motivation of the partition that's proposed by the paper. To separate high and low memory intensive applications makes sense, as well as separating high low buffer hitting applications. Why the separation by number of applications first, and then by the bandwidth requirements? Does the paper? Well, I think I'm not sure if the paper. I think the paper discusses some other metrics to separate, but I mean, you cannot write about everything that you tested. But these are things that work basically. So the number of applications is really to protect those applications, because if you, as I mentioned, if you actually partition by bandwidth requirements, you may actually have one very intensive high bandwidth application. If you try to balance the load between different channels, you may actually have one very intensive application escaping into a channel where you want to isolate the low intensity applications. And as a result, you may be back to square one or close to square one, let's say. That's the reason why you have you partition based on applications. But again, these metrics, again, you can always question the metrics. This is one incarnation of a general family of ideas, I would say. You can come up with some other metric to partition applications based on bandwidth requirements that do it in a non-balanced way. As long as you can come up with a nice way, that sounds good. Okay. Okay, feel free to ask more questions also. Okay, otherwise I'm going to assume that we don't have more questions. And that brings me to my last slide. So this time we've covered everything within 1 hour, as you can see. Although I took longer with the summary because I wanted to give some background also. Okay, well, if there are no more questions, I think we will be done early today. And next week, Mohammed is going to cover one other paper. That's going to be a different paper. Hopefully it'll be interesting still. And then I think at some point we'll start with the presentations. That's going to be 2 weeks later, I believe. Mohammed, do you have any announcements or anything to say?
I would just encourage everyone to start contacting mentors as soon as possible, because it will take time to schedule a meeting in this busy time. And that's all I think from my side.
Okay, so I will take one more question, I think, from YouTube. I think it'd be good if someone actually takes questions from YouTube, because there are some good questions also. Like, how do you think about processing in memory affecting this? Well, I think it's also interesting. Processing in memory, how does it affect this? I think in processing in memory, again, you have the interference problem. If different applications are mapped to different parts of memory, you may want to actually partition them to different channels again, so that you get the best benefit without interference from different applications. So I think this idea is actually synergistic with a lot of processing in memory, let's say, proposals and ideas. You don't want to be interfered with some other application. But I think that needs to be investigated more, how to provide quality of service when you have multiple applications accessing or doing computation inside the memory. Certainly that's important. Okay, I think that's all I will take for now. Maybe in the future, TAs can copy paste questions from there so that we can answer the interesting questions. Okay, so we're done. I guess have a good Friday and the weekend, and I will see you next Thursday discussing a different paper. Take care.